Today's lesson is going to be about finding segment lengths in circles. And the last example we're going to see, again, the reason we use this so much is for indirect measurement, and you'll see an example of that at the end. Okay, so when two chords intersect in the interior of a circle, so you can see we have these two chords here, and they're intersecting right there in the inside of the circle, in the interior. Each chord is divided into two segments that are called the segments of the chord. So it's really simple. DE is a segment, and EC is a segment of the chord DC. So if two chords intersect in the interior of a circle, then the product of the lengths of the segments of one is equal to the product of the lengths of the segments of the other chord. So in this case, you have EA times EB, that's the product, is equal to DE times EC. Okay, so we can apply that right down here to this question, right? They say find ML and JK. So what they want to know is what's the whole length of ML and what's the whole length of JK? Well, what we know is that if I take the segments of ML, MN, and NL, and I multiply those together and I get the product, it will be equal to the product of Kn times Nj. If I take those segments and I multiply them together, the product should be the same. So what that leaves me with is x plus 2 times x plus 1 is the same as x times x plus 4. So now all I have to do is distribute to solve or to expand these binomials. So a little refresher, x times x is x squared, x times 1 is plus x, 2 times x is plus 2x, 2 times 1 plus 2 equals x times x is x squared, x times 4 is plus 4x. Okay, so let's combine any like terms that we have. I have x and 2x, so that is 3x. So I get x squared plus 3x plus 2 equals x squared plus 4x. Now all I'm going to do is just shift things around to get x isolated, and so I can subtract x squared from both sides, so that's gone and that's gone. Now I can subtract 3x from both sides, and I'll end up with 2 equals 1x, because I'm taking the 3x away from the left, and if I take 3x away from the 4x, I just have the 1x left. So x is 2. But what they're actually asking for is what's the length of ML and JK. So ML is x plus 2, which is just 2 plus 2, plus x plus 1, which is 2 plus 1. And that's 2 plus 2 is 4, plus 2 is 6, plus 1 is 7. So ML is 7, and KJ is x, which is 2, plus 2 plus 4, which is 2 plus 2 is 4, plus 4 is 8. So there you go. Next, tangents and secants. So a secant segment is a segment that contains a chord of the circle. So you can see this secant right here. That's the secant. But it contains this little section, which is a chord of the circle. Okay? The part of the secant segment that is outside of the circle, this part is just called its external segment, but it's still a part of the secant. And then so the theorem for secants that we have here is that if two secant segments share the same endpoint outside of a circle, and you can see here they do in E, then the product of the lengths of one secant segment and its external segment, so meaning the whole thing, EB times EA, right, which is what you see here, equals the product of the lengths of the other secant segment. Again, it's not just the pieces, it's the whole times the external segment. So again, EC times ED. So those two products are going to be the same. So we have a little standardized test practice down here, and they're asking you to find the value of x, and we're just going to apply what we just learned. So we know that PR, the whole thing, right? So this whole thing is 9. And this whole secant segment is x plus 3. So remember, in this case, we're finding the product of the whole secant segment times the external portion, the external segment. So PR is 9 times 4, its external segment, is the same as the entire TR, which is x plus 3, times its external segment, which is 3. And notice I wrote this on the right just because of going in that order. This is no different. Normally you'd see that on the left. It's no different there. We can still distribute it. You could rewrite it back on the left if you wanted. You could move it over there, but it doesn't have to happen, right? So 36, 3 times x is 3x. 3 times 3 is 9. All I got to do is subtract 9 from both sides. I get 3x equals 27, and x equals 9, and D. Okay. So, segments of secants and tangents. So now we're mixing. We have a secant, we have a tangent, and the rule is very similar, but just notice there's no external segment of a tangent. EA is the tangent, right? And it's not going into the circle. It's just touching the circle at A. So again, you're not going to be able to find, there's not going to be an interior part of a tangent. So keep that in mind as we read this theorem. If a secant segment and a tangent segment share an endpoint outside a circle, E, then the product of the lengths of the secant segment is the same so far, right? The secant segment is ED times its external segment. So right there, right? We're multiplying the whole secant segment times just its external part. And that product is the same as the square of the tangent. So just the tangent times the tangent, okay? We can apply that right down here because they're asking us to find RS. And RS is just the external segment. Well, again, I know that if I multiply RT, the whole secant, times its external segment. So I'm going to do that. I'm going to say x plus 8, which is the whole secant. And if I multiply that by its external segment, which is just the x, and I'm going to put that in front this time. I know that that has to be the same as the tangent squared. That has to be the same as 16 squared. So x times x is x squared. X times 8 is plus 8x, and 16 squared, I feel like I remember this, but I want to make sure, 256. Okay, and so now we just have to solve for this. So when you have a quadratic, what you want to do is you want to get it set equal to 0. So what I'm actually going to do is I'm going to subtract the 256 from both sides, and I'll get everything on the left side, plus 8x minus 256. Equals 0. All right, and so to factor it or to find the roots of the equation, the possible values for x, we could do a couple things. I think the best thing is to graph it. So I just went over here, I put it into Desmos, and I wonder if this little marker is going to work over here. No, it doesn't. So you can just, if you look on the right, I have x squared plus 8x minus 256, which is what we had here, what we set equal to 0. And again, what we're looking for is what are the x values, meaning if we go left or right, where the function equals 0. Well, the function equals 0 anywhere where it crosses the x-axis. And we can see there's 2 points where that happens. It happens right here. The y value is 0 when x is negative 20.492. Or it happens right here where x is 12.492. And so those are the two possible values for x. But if you look at the equation, x has to be a positive value. It has a physical length. A length can't be a negative, right? You can't be negative 2 feet tall. So the only one that's going to work for us is the 12.492. So that means that x is 12.492. And the other way, and this is an approximation, the other way that you could have done this is you could have used a quadratic equation, right? And if you used the quadratic equation, you would have ended up with it in radical form, which is either way is totally fine. I always prefer to do the graphing because I can visualize what's happening here, right? I can see the parabola, I can see the arc, and I always like to do that the best. Okay, one last question. So I think I'm just going to move this back to full screen. All right, and so as I said at the beginning of the lesson, what we generally use these things for, as we developed math, what we were trying to do was understand our world, our universe, and most of our universe, the planets, the cosmos, all the galaxies, the atom, most of it is spherical or circular, which we use the circle to represent these spheres, and the reason is because of the force of gravity. So everything is, it's the most dominant shape in our universe. And so we need to understand it, and one of the reasons we want to understand it is because we can use those understandings to make measurements of things that we could never measure by just taking out a tape measure or something like that. So here's an example. So Tethys, Calypso, and Telesto are 3 of Saturn's moons. Each has a nearly circular orbit, 295,000 kilometers in radius. The Cassini-Huygens spacecraft entered Saturn's orbit in July of 2004. Telesto is on a point of tangency. So again, a point of tangency right here. So you can see it's right on a tangent of that circle. So Find the distance dB from Cassini to Tethys. So you're trying to find dB is this whole thing. Well, we're just going to apply what we just learned. We know that the product of this whole secant times its external segment, right? If I multiply that, so I could call BC, maybe we'll just call it X for now. So we can call that X. So I know that if I take the whole thing, X, I might as well write X, plus 83,000. Start that over, make it look nicer. X plus 83,000. If I multiply that by the external segment, the 83,000, that's going to be the same as this tangent squared. So I'm just going to put that at 203,000 squared. Now notice these numbers are going to be gigantic, but that's totally fine. There's nothing wrong with working with large numbers. So I'm going to have 83,000x plus 83,000 times 83,000. So 83,000 times 83,000 is this gigantic number, 6, 8, 8, 9, and 1, 2, 3, 4, 5, 6. I think I got that right. 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6. So right there, right there. Equals, now this is going to be even larger, 203,000. Right, so 203 times 203. 41209, and then we're going to have 1, 2, 3, 4, 5, 6. So just confirm that I had that right. 10. Yeah, okay, good. All right, so now we're going to just subtract this 6889000. So what is that again? Millions is billions. Subtract that 6.9 billion from both sides, and we will get 83,000x equals. So now let's go back to this gigantic number. And what is that again? That's just trillions. No, 41 billion. So 41 billion 9,000,000 minus 689. And we get 3, 4, 3, 2, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. And that looks correct. Okay, and then we divide by 83,000, x equal. Remember, these are going to be large numbers. We're talking about orbital distances. We get 41349, and we'll just round up to 4. So it is 413,494 kilometers. That distance x. But you wanted to actually find the distance dB. So dB is the 413,494 kilometers plus the 83,000 kilometers of the external segment. And that is 496,494 kilometers. And that's an approximation.